5.6 Rational Functions. This is where kind of chapter 5 all comes together. This is what we've been building for. What's an intercept? What's our domain? What's our zeros? What's our multiplicities? We're all going to put them together. So if any of those terms I just mentioned sound foreign and terrifying, make sure you kind of go back and review them. Or if you get lost along this video, definitely a good time to pause and go back. We have covered everything except for maybe 2 or 3 concepts in this section. We're just putting it all together now, so it can be pretty overwhelming if you were feeling not great in a certain section. Okay, so end behavior, we definitely talked about end behavior before. We've mainly been talking about this first case. So the as x goes to infinity, we look at our graph. So in this case, if I look at my graph and I'm saying, well, what's happening to the right end of it? Well, it seems my graph's going to 0. That makes sense. If I look at the left side of my graph, okay, well, that's also seeming like it will go to 0. The other type of end behavior that we talk about is not necessarily at the ends of our graph, but kind of as we're approaching a number from each side of that number. And so this is going to be pretty helpful when we get into the graphing and everything like that. And I believe this was a question on the last semester's test 3 or midterm or whatever we're on at this point. So it is worth mentioning. So if we look at this graph again, and I can kind of see, okay, well, nothing really exciting is happening until it seems like when I get to 0, and then my graph shoots up in one direction and shoots down in the other. So I can describe that end behavior of like, I don't know exactly what's happening at that point, but I know as I get really close to that point, what my graph is approaching. So with the notation that we see on the second as, so I have as x approaches 0 with a positive superscript, comma, f of x goes to infinity. So that as x approaches 0 plus, that means I'm approaching 0 from the positive side of my graph. So the positive side of my graph is the right side, and I'm approaching it, so I'm moving to the left up to that value, and then as I get close to that value from the right side, boom, it shoots up to infinity. Where, kind of similarly, as x approaches 0 negative, well, that means I'm coming from the left side. So as I approach from the left side, my graph shoots all the way down towards a negative infinity. So that's the 2 ways we kind of talk about end behavior, as we talk about the endpoints towards the left side and the right side, and then kind of the endpoints when we get close to a value and something weird happens at that value. I mean, we could honestly talk about any value. It's just not particularly interesting to talk so much about, like in this case, what's happening as x approaches 2 from the positive side. Now, maybe a bit of review, finding the domain. So the domain of this function, this is a case 1 function. I set the denominator equal to 0 and I solve. Okay, well, x squared plus 5x plus 6 factors to this, x plus 2 times x plus 3 is equal to 0. And so we know when we were talking about domain that x can't be negative 2 and x can't be negative 3. Now, when we're talking about graphing these things, when we're talking about graphing these fractions, to account for the fact that x can't be negative 2 and negative 3, I introduced this concept of a vertical asymptote. And so what a vertical asymptote, how that works is I draw a vertical line on those values and I say, okay, whatever my graph looks like, we'll maybe be able to connect the dots later, but whatever my graph looks like, I definitely can't have a graph that would ever touch this line. And so that's something cool about vertical asymptotes, is that you will never ever cross them, you will never ever touch them, at least what you'll see in this course. And so when I'm kind of putting that in a graph, I tend to draw them with those dotted lines. So it's a reminder saying, okay, when I have a graph, I'm not going to cross these, I'm not going to touch these. These are almost like they're breaking up my graph in 2 separate pieces. So we call those vertical asymptotes. And we typically don't write the x not equals to negative 2, negative 3 at this point. Yes, you can write it. No, I won't dock you. But when we talk about vertical asymptotes, we're actually describing that line. And so that line is just x is equal to negative 2. It's a dotted line, but it's just x is equal to negative 2 and x is equal to negative 3. That's kind of an intro. This is one of the new concepts from the section, and we're going to tie it into putting everything together. So it might make sense to think, okay, if I have vertical asymptotes, probably have something called a horizontal asymptote. We do. The process behind it is a little bit more involved. And so kind of falling into the theme of there's different cases. With horizontal asymptotes, there's 3 cases. The nice thing is 2 of them are really easy to deal with, and the third one we generally don't talk about in this course because it's a bit of work and so it won't show up on a test. So case 1. Case 1 is if I have a fraction, if I have a rational function, which is just a fraction, and the degree of my denominator is bigger than the degree of my numerator, I have to do 0 work and just say y is equal to 0. You want to show your work if you're taking a test or something like that. It's perfectly fine for you to just say case 1, y is equal to 0. That's fine. So as an example, f of x is equal to x over x squared plus 3. Yeah, I could potentially find horizontal or vertical asymptotes. That's not what the question's asking for. But the degree on the bottom is 2, the degree on the top is 1, so voila, horizontal asymptote, y is equal to 0. Great, that's the nice case, and that's the majority of cases that you'll see. The slightly less common, but still will show up, I believe we worked through an example of this case, is that if the degree of the denominator is equal to the degree of the numerator. So in order to find that, or the process to kind of find what the horizontal asymptote is at that point, is you set the leading coefficient of the numerator over the leading coefficient of the denominator, and then maybe do a little bit of simplification, but that's your horizontal asymptote. So again, it's going to be y is equal to some value. So to see that in practice, that's a very overly wordy explanation, I know. To see it in practice, not too terrible. Here I have a rational function. My degree on the top is 2, my degree on the bottom is 2. My leading coefficient on the top is 3, it's what's next to my x squared. My leading coefficient on the bottom is 2. It's what's next to my x squared. I don't really care about that plus 3. That doesn't affect my horizontal asymptote. So take those 2 numbers, put them over each other, reduce them if need be. In this case, they don't reduce. It's just 3/2. That's your horizontal asymptote. Okay, case 3. Like I said, you probably won't see this. Worth mentioning, though. Maybe there will be something on WebWorks because, you know, WebWorks is WebWorks. So this case is that if your degree of your denominator is smaller than the degree of your numerator. And in this case, this isn't technically, it should be case 3. Oh well. In this case, it is not actually a horizontal asymptote. We call it an oblique asymptote, which is kind of just a diagonal line. And so you find this oblique asymptote by using synthetic division or using polynomial long division, and then it's whatever the quotient is. So what that means is it's everything up to that remainder. I don't really care what the remainder is, so it's everything besides the remainder. So to see that in practice, here I have f of x is equal to 2x squared plus 3x plus 1 over x plus 2. The degree on the top is clearly bigger than the degree on the bottom, so I can't use those first kind of neat tricks from case 1 and case 2. Instead, I'd have to do synthetic division or polynomial long division. I think I just skip the process and jump to the answer, but if you divided that out, you would get 2x minus 2 plus some remainder, which I don't care about. And so my oblique asymptote would just be y is equal to 2x minus 2. Like I said, if this was something that I was almost certain was going to be on the test or even on the in-class worksheet, I would probably explicitly go through the synthetic division, but we've seen that probably 3 or 4 times at this point. And really, it's just the fact that the result would get us an oblique asymptote, our oblique asymptote. Okay, so now we're going to combine both of these concepts, put them together. Finding horizontal and oblique asymptotes. So I think the first step I'm going to do with this rational function is find my vertical, if I remember correctly. Okay, I set the bottom equal to 0. I factor, and so I know my vertical asymptotes are x equals -3 and x is equal to -2. I think this is honestly what we found on the first slide or the second slide. So I did rush through it a little bit, but same concept. Factor, set it equal to 0, solve. Those are our vertical asymptotes. Now for our horizontal, since this is new, we'll kind of slow it down on that one. It's a case 2. How do I know it's a case 2? Fair question. I should probably FOIL it out. So I FOIL out the numerator. X minus 4 times x plus 4 is x squared minus 16. And I have that 2 in front. And now I can see the degree on the top is equal to the degree on the bottom. So I know I'm in a case 2 scenario. And so I would distribute the 2 out, and now I look at the coefficients of x squared and x squared. And so there is kind of that invisible 1 next to the x squared in the denominator. So it's just 2 over 1, which is just y is equal to 2. Now, something that is worth mentioning is that vertical asymptotes do have multiplicities, just like we saw when we were talking about zeros or intercepts previously. And so process is still the same. If we're trying to find the multiplicity of vertical asymptotes, well, it matters what vertical asymptote we're talking about. So we have to find those asymptotes first, and then we can talk about their multiplicity. So we start by setting the bottom equal to 0, solving, okay, x plus 1 equals 0 is -1, x minus 1 is equal to +1 if you add 1 to both sides. And now the multiplicity, well, you can just look at each of those factors. So x plus 1 has a multiplicity of 2, x minus 1 has a multiplicity of 3. Again, all of this should feel somewhat familiar because this is exactly what we did when we were trying to find the multiplicity of zeros, or when we were trying to find the multiplicities of x-intercepts. But what's different now is, what does this mean? So if we recall with the x-intercepts, what it meant is that you would either cross the 0, or you would bounce off the 0, or you would do a wiggle through the 0, where here it tells us what's happening kind of at those dotted lines. So we saw on the first side and we saw on the second slide that it seems like our graph either goes all the way up or all the way down when we're at a vertical asymptote. And that's exactly right. Vertical asymptotes, that's going to be how they behave every time, is as you get close to it, either your graph's going all the way down to -infinity or all the way up to +infinity. And so the multiplicity of a vertical asymptote tells me that at that line, once I kind of draw it down to -infinity or up to +infinity, once I make the decision, let's say down. So once I go down to -infinity, if I have an even power when I pick up my pencil to move it to the other side of the vertical asymptote, it will end up on the same side when I start writing again. If it is odd, once I finish kind of moving my pencil all the way to the bottom side of my page, and I pick it up because I can't cross my vertical asymptote, I move my pen to the top of my page and restart drawing my graph. So even multiplicities mean that your graph's going to be on the same side of those vertical asymptotes. Odd multiplicity means they're going to be on opposite sides. And notice how I'm saying even and odd. I'm not talking about degrees of 1 or 2 or 3. It could be a power to the 7th. It could be a power to the 20th. It's always going to behave this way if it's even power or an odd power. So let's see an example of this. So here's a graph of what f of x would look like, the very same one that we were talking about on the top left of the slide. And yes, this is kind of pulled from Desmos. So this is what Desmos would graph. This is what your graphing calculator would graph. And this is technically what the graph is. But as a reference point, we're going to put in our vertical asymptotes because that's how it's good. That's how almost everyone graphs it by hand. They kind of say, cool, I know these dotted lines don't technically exist because it's not supposed to cross them at all, but let's just put them in so I know where to kind of draw things. So here are my vertical asymptotes entered in. So if I'm going from left to right, I'm going to start drawing my graph, and then I come to my first vertical asymptote, and it's either going down or up, and we're going to talk about how you determine that part later, but for now, it goes down. So it goes down, and then I draw my blue line to the bottom of my paper, and then I can't actually cross that vertical asymptote, so I do have to pick it up at one point. So when I pick it up, I look to see, okay, do I keep my pencil on the bottom of my paper, or do I move it to the top? So I look at my multiplicity. The multiplicity is 2. I keep it on the bottom of my paper, so I just move my pencil to the other side of the asymptote, and then I continue to draw my graph. And then now I come to my next asymptote, and it ends up going down. So I go draw to the bottom part of my paper, and then I say, okay, what are we doing here? Is it, what's my multiplicity? It's an odd multiplicity. It's a multiplicity of 3. So I pick up my pencil, and instead of directly moving over from the bottom of my page, I have to go all the way to the top of my page, and then I move to the other side of my asymptote, and then I draw my graph. So that's really what it's talking about, that same side versus opposite side when we're graphing. And yes, this will be valuable when we're trying to put all of the pieces together.